All right. So, hi everyone. This is going to be the last talk in the second session of the Quantum Science Day. And this is going to be given by Akash Kundu. And he's going to speak about optimizing the production of test vehicles using hybrid constrained quantum annealing. So this is also related to a QIntent project, is it?
Not actually, but it was
No, it's not.
kind of interesting. I'm going to talk about it because there was a BMW challenge. It came out like last year, October or something, and not last year, February. And we tried to tackle this problem, and we found this problem very interesting. And we got some interesting result to publish on as a preprint on archive. So I'm going to discuss about this eventually. And yeah, so we have now music. We can produce music using quantum, but where we can play the music, right? We need cards. And to produce cars, we need to test on cars, and to do some test, we need to produce test vehicles. And that's why this work, probably, that optimizing the production of test vehicles using hybrid constant quantum annealing. And it's a mouthful of title, but I'm going to decompose it. And I'm one of the co-authors, along with Adam Gross and Muslim. And we are all from the Institute of Theoretical and Applied Informatics, Polish Academy of Science, and this is our beautiful logo of the institute. So next, let me start by talking about optimization problems from the initial. So this is basically, as most of you know, and we're talking about in last 4 or 5 sessions, that optimization problem is basically finding the best solution from all the other feasible solutions. And to find the solution, we basically do is that we encode the problem into objective function, and we try to minimize it under the environment that there are some constraints, which are basically in terms of equality and inequality constraints in this particular form on the down right side of the screen. And then we can actually decompose this particular optimization problem into 2 parts. When this fx, which is objective, and the constraints are all linear, then the problem basically looks like this, and it is a very general description of the problem. And this is basically called a linear programming because the objective function and the constraints are linear. And then at this particular setting, when this particular variable of the objective is integer, then we call it integer linear programming. And when the variable is 0 1, we call it binary LP or 0 1 LP, linear programming problem. But at the same time, when this objective is quadratic and the constraints are linear, then we call it quadratic programming. But in this problem, we tackle something else, which is basically called quadratic constraint quadratic programming problem. So, and in that case, we have constraints as well as this objective function, both are in quadratic formulation. So next, I'm going to talk about the problem in the nutshell. So, which is basically we have a list of tests which we need to do on the cars. So that's why we require cars with certain features, but we need to find the minimum number of cars that can cover as many tests as possible, obeying the configuration rule. So a car has a configuration rule. We are going to talk about it in next 2 or 3 slides. Now let me talk about in more detail about the problem. This is basically like, the big car companies, they introduce new cars each year with new features and new, maybe new features, basically like a car having a slide door or not, a car having a cooling door or not, or something like that. So to introduce the new feature, to introduce a new car with that particular new feature, we need to do some specific test before the production of the car, because maybe the production of the car will be faulty. So that's why we need to see the validation of the car's model's functionality with that particular new feature introduced by that particular company. So this requires the production of test vehicles, basically, and there is a challenge. That's why we are talking about this problem. And this challenge is costly and complex, like all the problems in combinatorial optimization. And the solution can be given by that simply by minimizing the number of test vehicles that can cover as many tests as possible. So to do this, we have this problem. And we have some constraints, buildability constraints, and this will look like a lot of things, but I'm going to talk about them in a few minutes. So we have this single type constraint, and then we have feature allowed per type constraint, then we have group features, rules per type, and these all are called vehicle configuration rules. And this actually decides that which kind of configuration will a vehicle have. And then we have something called like test requirements. which in our problem we encode as the objective, and the buildability constant, as you can see, are the constants that has been that has applied on the objective. I mean, we solved the objective, which is test requirements, under the buildability constraints. And this is basically the test requirements of the properties of the car needed for the particular testing phase. Next, so this particular problem arrangement was actually given in the BMW Quantum Computing Challenge. But the problem we are tackling with is a very general problem for any kind of production house, you can say. So BMW Quantum Computing Challenge gave us the opportunity to actually deal with real data that is available by a very, very big company. So, so we propose this solution, which is basically the number of minimizing the number of test vehicles that cover as many tests as possible. And to do this, we basically encode these features and also the constraints as Boolean variables. And when you have this particular formulation, then we optimize. Then we have this optimization step, right? Then in this optimization step, we use this classical and hybrid quantum solvers. And let me give you a small idea that what are the Boolean variables, what are the encoding is. Basically that we formulated the problem into integer linear programming. That's why I give you this particular introduction to this integer linear programming. So these variables we introduce as a feature and also as a test are basically integers. And the problems we had are basically the constraints and as well as the objective are linear. And then our goal is basically is to achieve the above encoding with as few qubits as possible. And the proposed solution we have that the variable number grows with O of this particular unidentified variables, right? But just focus on this particular n, which is basically number of test vehicles. And as you can see that as we increase the number of test vehicles for particular list of tests, then this variable number grows linearly. So this is very good. You can say this is very good, right? I mean, increasing everything linearly is a complexity wise good. So what is the ways of analysis of the problem? So we have this encoding and we approach two ways, set, and this but basically answers that are there any n cars, which we have a n car, n number of cars that has been fixed sufficient to cover all the tests from the list of tests. And then we have this next set problem, which actually minimize works with the objective function and the constraints. And it aims to maximize the number of tests covered using n test vehicles. I mean, maximizing and minimizing is basically like putting a sign reversal in the objective function. So this is like an equivalent problem, you can see. So next, I'm going to talk about this set and max set problem. And we, as I told you, that we optimized in a classical and quantum classical way. So for classical, we used CBC and Gurobi solver. And the CBC is basically coordinate bunch and cut. And we use this classical plus quantum is the hybrid solver from the D-wave. Now this CBC and Gurobi solver actually was used as a benchmark for this particular quantum hybrid solver. And there are many hybrid solvers that is made available by this D-wave, by D-wave company, and one of them is CQM solver. So CQM is basically constant quadratic model solver. And CQM is, as I told you, newly introduced solver in D-wave's hybrid solver service, along with DQN and DQM, which are discrete quadratic model and binary quadratic model. So CQM solver implements a classical frontend because it is a hybrid and works with a quantum backend. And we talked about this hybrid approach, and this is basically the workflow which has been just given by which has been given in the white paper. And as you can see, this solver takes input and then it goes through this classical solver, and this quantum module sends this classical output to this QPU, which is basically does this so-called quantum annealing process. And that's why it is basically classical and quantum front-end and back-end, because classical is front, quantum is back. And to be honest, like we actually don't know the specifications of how CQM actually works. So like the inner mechanisms, but we know that this is basically the workflow of it. So the CQM solver works with an objective which is quadratic, and also at the same time it works with a constant which is also quadratic. So this is like basically a very different solver and very efficient solver, because this actually takes these quadratic formulations of the objective and the constants, and where all the coefficients are real, And this advantages is that sequence solver natively supports equality and inequality constants. And this less number of variables, because as Ludmila presented in a slide, that there is a penalty method because we have this inequality constants, we need to make them equality. But we don't need to do this in this sequence solver, so that's why we need less number of variables. And 3, it allows quadratic constant directly, so which is not possible in the quadratic constant quadratic unconstant binary optimization problem, because we need to make the problem as unconstant. So next, we are going to just restate this once again because we may forget this structure. And then this is a statistics of the number of constants that has been given provided by this BMW challenge. And as you can see that we have this rules per type, which is more than 4,000, and test requirements, which is more than 600. And it's a very huge number of constants. We need to, and in this case, we need to solve this particular objective, which is encoding test requirements. So I'm going to decompose, like talk about each and every one of them right now. So this single type requirements is basically saying is that each car should have a single type. So a car cannot have more than one type. This is basically like a logic, right? This is a very simple concept. So that's why we have this particular Tij, which is here in cheats I have defined, where this Tij, when Tij is 1, that means that this vehicle I has a type J. That's why if for a particular vehicle I, if we go through all the types, then the sum should be at least 1, because each car is allowed for only one type. And then we have this group feature, which is basically saying that if we have a set of groups, then we have this particular collection. From the particular collection of groups, each car have at most one group, one feature available from one group. So that's why this is upper bounded by this less than equal to 1, and this Bij is equal to 1 when the vehicle I have this feature, vehicle J. So that's why it is upper bounded by 1, because each car cannot have more than 1. So, and the next is basically for a given type, only one of the features, only some of the features are available. That means we can have this. So we formulated this in a specific way, that is, we consider that there can be some possibilities where some types are available, but the features are not available. That means that this Tij we defined is maybe 1, but the Bij can be, Bik can be 0, right? So that's why it cannot, it is also upper bound. The sum of these two variables are upper bounded by 1, where I equals to n. This n is the number of test vehicles, j is different types available, and k is this particular fj, and fj is number of test vehicles. So fj is basically the collection of features. And then we have this rules per type. As you remember, it has more than 4,000. So I'm not going to waste. I mean, I don't have enough time to talk about it, to be honest. I want to talk about it, but I cannot. So this is basically like the implications about the presence and absence of features. And this is basically in this particular form. Let me read what is basically written here. So F2, F3, F4 are basically like the features, number of features. And F2 can be like the sliding door, or maybe like a rooftop or something like that with a car. So this is basically like Ti, this particular car with type 1, with feature F2, not having feature F4 and F5, implies that it must have either feature F1 or feature F3. So this kind of conditions we had more than 4,000, and we had to decode it into a logical expression using these binary variables. And when we did that, it is basically looks like this. So yeah, this looks quite messy, but in our archive preprint, I'm not going to read through it, but in our archive preprint, I'm going to give it access to you, like the link. We have a very good description of it. Next, we have test requirements. So we just assume that test J requires kj amount of cars. Then this can be solved using this max set. As you know, that max set requires a particular objective function. And for a particular test, we actually define this particular variable Pij, which is 1 if the vehicle I used in this particular test J, and we introduce this weights Wj. But this is just like a general formulation, right? But in the problem when we solve, we basically use this weights as unity. So we give all the tests as equal weights, and then what will happen if the particular test requires, I mean, more than kj cars, right? Then what we just introduce. So it shouldn't add to the objective, because it will just help us. It will not help us to reach the optimal solution. That's why we introduce this particular constraint, which is basically this Pij, this vehicle I used in test J should be less than equal to kg, upper bounded by this number of vehicles kg. And then we have this set problem, which is basically this number of tests should be equal to at least should be equal to the number of cars required in the set problem. But we solved it in the so we're going to show the results for this next set. And then we have this problem resources. So if we have f number of, so n is the number of cars, right? N is the number of cars we used. So if number of test vehicles, if f is the total number of features, then n dot f is the binary variables which gives the features for per car, and n dot o is the basically like the types, o is the total number of types, and so this number of variables of defining types for each car, and n dot q is basically like the test required for each car, and the total variable we have is basically by compilation of all of them is o n f plus o plus q binary variables we require. And this is quite good because this is at most quadratic, right? If we have with the number of vehicles, so this is quadratic in the form, and quadratic increasing quadratic way, the variables are not complexity wise not bad. And right now you know that what is this f, o, and q means. So let us proceed to the algorithm we solved the approach. Is basically this global bisection method has been introduced in the BMW's approach, and the idea was basically used to we will start with a very huge number of cars from the list of tests, and we are going to try to use this particular binary search to find out the optimal n. But the problem with this approach is that if you start with a very huge number of n, so that there is no upper bound, right? So the large number of variable requirements, because the sequence that I introduced, I talked about, you have introduced, allows more up to 5,000 variables. So we cannot just put any huge number on n. And at the same time, this Gurobi has no limit, the classical solver, which is used for benchmarking, no limit in the number of variables. But as you know that if we increase this n, then it will not be efficient with respect to time, right? Because it will take a lot of time to solve. And then we have this vehicle greedy algorithm, also we talked about it. I mean, greedy algorithm, not vehicle greedy, because. And then the idea of this algorithm that we introduce this n bunch, which basically says that number of cars that will be configured at each iteration. Then after one iteration, the tests are updated by removing satisfied one. So if n bunch equal to 1 considered, then we are configuring one car for all the list of tests. And if that particular car satisfy tests, then we are just removing that tests from the list of tests. And right now we have a reduced number of tests. That's why we require less cars in the next iteration of the optimization. So with this updated number tests, we are optimizing again. So that's why each and every time the optimization procedure is getting reduced. And to be honest, there is no promise that this vehicle greedy algorithm is going to algorithm is going to give us the optimum. But this is a better approach compared to this global bisection method, using considering the resources we have. Numerical results. Let us go through that. So n1 equal to 1 is basically we configuring one car for this at each iteration. So we have this particular plot and with number of remaining tests per iteration. So as you can see that the CBC solver, we have this classical solver, it has the smallest number of vehicles that required to solve all the tests that is available. This Gurobi returns 64, 2 more cars it requires. But the sequence solver actually stops at 65. But the problem is that the sequence solver couldn't find a solution couldn't find that one car that could solve this particular one test that was remaining. So we just infer that probably 66 cars will be enough for the sequence solver to satisfy all the tests. So that means, yeah. But next, we have this particular runtime for these solvers, and we use this CBC and Gurobi for benchmarking. So as you can see, sequence solver takes more than 5 minutes. These are all in seconds, and this is expected because it was like the processing time from these heuristics to this quantum module. So yeah, but it is good, and this was our result. And actually, we believe as authors, we believe that this was like the first time, this was the first work that has been done to benchmark this particular sequence solver available by this DOF. So yeah, and that was my result, and that was we optimized cars, number of test vehicles for a list of tests that has been available by BMW, and these are the references I used. We used, not I, we used. This is the DOF and hybrid solver introduced, and this BMW. And last, this is our paper, which is in archive, and also the codes are available to reproduce the results and also generate new results to test with it. And this is the code in Zenodo. And so thank you very much for your attention.
Great, thank you for the talk. There are two questions from Iman. So I was asking, is this work published somewhere, or do you have it on preprint?
Yeah, actually, it is submitted.
Oh, now I see it. Yeah. Sorry, I missed. I was trying to get from your last slide. Okay, so it is there on the.
Yeah, it is on archive, but it is submitted in some journal also. So yeah.
I guess it's a general interest. And the other question is, so the classical part, what algorithm was used for solving the problem? Is it a local search or any other meta heuristic?
I think like if you say like the sequence solver, the classical part, to be honest, we're not sure about that, because in the white paper they don't talk about the decomposition of the classical and quantum module. So we just know that it passes through this classical and quantum, but we don't know like which kind of particular algorithm they are using in the classical part. So yeah. So I cannot answer that. Sorry.
Yeah. Okay. Great. Great. Are there any questions? I'm having a look at the. Okay. It seems there are no more talks. So let's thank Akash for this excellent talk. And this is the end of the second session. See you in the next session, which should be starting in about 35 minutes. But if not, then the organizers will jump in and